From our discussion of the oscillating conditions associated with brine sheets and shallow water halites in the previous chapter, I now want to move to the Dead Sea, which includes the deepest brine sump anywhere in the world. In fact, the Dead Sea defines what is the deepest continental position. The surface of the Dead Sea today is about 440 meters below sea level. It's the deepest continental position in the Earth's current terrestrial surface. It is our only example in the modern where we have halite accumulating in waters that are more than 300 meters deep. So it's our only modern analogue for deepwater halite deposition. In the last 2 decades, it's become a very significant laboratory for looking at the processes that drive the accumulation of various styles of halite in deep water. The Dead Sea is about 80 kilometers long and 20 kilometers wide. Its area is around 800 square kilometers. It has a brine volume a little under 150 cubic kilometers with a catchment of around 40,000 square kilometers. Its current surface is about 440 meters below sea level. That current surface level divides it up into 2 basins. A northern basin, where in the sump of that basin we have halite saturated brines that are more than 300 meters deep, salinities in excess of 340 parts per mil. And a southern basin, which is now artificially maintained by pumping of brines from the northern basin into the higher level of the southern basin, where we have a series of carnallite plus halite precipitating anthropogenic pans on both the Israeli side and the Jordanian side of that basin. We can also see Mount Sodom, which is an outcropping salt diapir, and also the Luzon Peninsula, which is underlain by shallow salt. The bathymetry, the image on the right, shows that deep bottom in that northern basin, and that much shallower than 400 meters in the southern basin. In the 60s, that was a single body of water between the northern basin and the southern basin, but that brine level has been falling ever since. In fact, as we'll see shortly, in February 1979, that northern basin changed from a meromictic, a density stratified brine system. Once it went into that holomictic phase, we see the accumulation of deepwater halite on that 300 meter plus water brine column, or below that 300 meter plus water brine column in the northern basin. The northern basin is typified by a deep perennial saline lake system at halite saturation. The Jordan River makes a classic Gilbert-style delta on the northern margin, whereas the southern basin is a typical saline pan, now artificially maintained by brine pumping into those potash saltworks on the Israeli and the Jordanian side. The Dead Sea is a magnificent analogue basin for deepwater halite in the northern basin and for the types of chevron-dominated system we've previously discussed in that southern basin of the Dead Sea. In cross-section, you can clearly see where much of this salinity is coming from. It's coming from that Pliocene evaporite unit, the halite unit, which is halokinetic, the Yamura formation, being reworked into the brines of the Dead Sea. We can see that primary source of solutes, the Yamura formation, outcropping in Mount Sodom. There's Mount Sodom, there's Lot's Wife, which is a cap rock system. Here we're looking at that cap rock on top of that steeply inclined, isoclinally folded halite underlying that cap rock. This material is dissolving and supplying brine into the Dead Sea. We also have freshwater coming into the system from the Jordan River and from a series of arroyos coming into the margin of the Dead Sea. This hydrology has altered significantly since the late 70s, and in fact up until February 1979, that whole column was stratified. You can see in the 1864 density profile, the 1919 profile indicated by the lighter green and blues, we can see that upper stratified water body extending down to some 50 meters into the brine column. Then below that, a relatively homogeneous brine, almost at halite saturation, with a density in excess of 1.23. If we plot the history of that density stratification until it experienced overturn in February 1979, we can see back in 1959 it was densely stratified or meromictic with an upper density of around 1.205 and a lower density of 1.232. We follow that through into 1975, and then we can see that the halocline is deepening. We're still with density stratification. The upper brine mass had a density of 1.229 and the lower mass had a density of still relatively stable 1.232. Then in February 1979, the density of that upper water mass attained that of the lower water mass, and we had overturn. That then became a holomictic, a constant salinity water mass throughout the whole of that deepwater Northern Basin column. In core, there's evidence of an earlier overturn event, some 300 to 400 years ago, but we're focusing in on the hydrology in this current deepwater phase. Now, that transition from a density stratified meromictic system into a holomictic system drove a significant change in the nature of bottom water sediments from what were previously carbonate dominated with some gypsum lamanites into deepwater halite accumulating meshworks, typically without chevron inclusions in them, and a combination with founded rafts below a water column that was 300 meters of halite saturated brine. We look at the pre-1979 sediments on the bottom. These are typical lamanites. You can see they're dominated by stellate aragonite clusters and also some detrital calcite and other detrital material and clays forming laminated deposits. But that drop in water level and the transition into holomictic, and you can read the details on these water level changes in the book that accompanies this course, related to a lessening of inflow from the Jordan River and the pumping of supersaturated carnallite plus brines coming in from the salt works in the Southern Basin drove that loss of density stratification. But until the late 70s, that lake was density stratified, and we were forming aragonite calcite couplets on the floor of that deep stratified basin. We weren't accumulating halite. Then, once that overturn occurred in February 1979, there was a drastic change in what was accumulating on the floor of that 300-meter deep brine column. We started to accumulate halite, and these were clear, sparry, inclusion-free, centimetre-sized halites forming a meshwork, a crystalline meshwork, not the aligned zigzag bottom chevron halites, but a meshwork of inclusion-free halite, interspersed with a whole series of founded rafts. We'll look at the hydrology of those rafts versus the coarser halite on the floor of that deep water column a little later in this chapter. There's also a very obvious difference between the summer halite accumulating on the bottom of that deep water brine column and the winter accumulation, where a much finer grained halite mat accumulates atop that coarser crystalline halite. The other interesting thing is that once we core into the floor of the Dead Sea, around 4 meters below, we start to recover similar textures, these coarsely crystalline meshwork textures, but in this case with a much muddier surround. But these are clear, inclusion-free halites surrounded by muds. Some people have drawn analogies with halotubation textures, but these are subaqueous textures, and it's likely to have an age of around 2,500 to 2,800 years BP, perhaps indicating another time of holomictic halite saturation on the floor of the Dead Sea. These events are not unique to the current largely anthropogenic overturn event that's driving the change in the deepwater hydrology. There were natural episodes where this transition from meromictic to holomictic occurred prior to the anthropogenic interference in the inflow rates of the Jordan River drainage and the pumping of bittern waste brines back into the Northern Basin from the potash plants in the Southern Basin. So with this in mind, let's now look at the Dead Sea as the type example of how subaqueous halite accumulates in deep water evaporite sedimentation. But even there we'll see there's a seasonal temperature oscillation preserved in the textures and the halite that's accumulating on the floor of that deep water column. Let's just remind ourselves the Dead Sea physiography. In the Northern Basin, we are looking at a 300-meter plus brine column where we have deep perennial saline lakes, which is the focus of this chapter. In the Southern Basin, we have the saline pans with the carnallitite forming in those anthropogenic pans with textures very similar to what we discussed in the previous chapter for shoal water. Then around the margins where we have the interface between the alluvial fan inputs and the shallow perennial saline lakes, we have what's called a mixed halite facies, and we'll look at that in a separate chapter after this focus on the deep water halite. So there are 3 type environments in the Dead Sea, and we see a whole range of textures. We even see halite oods forming in the shore zone. We today see a brine column which is saturated in the Northern Basin. So if we put a steel cable into that brine column, we see halite crystals growing at various rates up and down that cable, extending all the way from the surface to the bottom, that deep water bottom of the Dead Sea. We'll also see there's a very obvious difference in saturation states between summer and winter in the Dead Sea. We see that also being preserved not just in that crystallization measuring steel column, but also in the nature of the bottom sediments that are accumulating on the floor. So let's have a look now at a video captured by the group Sirota and others working in those textures and in those hydrologies currently active on the floor of that holomictic brine column in the Dead Sea. So here we can see forming on the surface halite rafts floating on that surface. They require relatively stable conditions and supersaturation. As those rafts continue to grow in size and there's wind activity, they can founder and sink into that column. So let's look at what happens as we lower our camera now into that brine column, descending down into the deep water in the Dead Sea. Here we can see rafts floating in the upper part of the column and slowly sinking into the bottom, so they're foundering through the water column. Those rafts will then accumulate, of course, on the floor of the Dead Sea, providing there is supersaturated conditions on the floor of that Dead Sea brine column. Typical skeletal formed halites, we're now moving down toward the lake floor. We've now reached the lake floor, and here we can see those coarse meshworks. In this case, they're covered by a fine halite, and we can also see rafts accumulating. So we can see the settling of those halite crystals through the accumulation into accumulate on the floor of that Dead Sea column with a settling velocity of around 0.5 centimetre per second, with a typical grain size of the order of 0.1 of a millimetre. So coarse crystalline halite on the bottom with a cover of finer crystalline halite mixed in amongst founded halite rafts settling through the column. What's interesting is there are two parts to this hydrology. There is a summer control to the brine accumulation of halite, and there is a winter associated brine accumulation of halite. Around that thermocline, remember that this is a holomictic column, but we can still have temperature stratification, so that in the summer, when conditions are much hotter, things are heating up in that near surface position. We set up a thermocline, or if you like, using the lacustrine hydrology we talked about a few modules ago, a metalimnion separating the upper water mass, the somewhat warmer water mass in the summer, epilimnium or the upper brine, from the somewhat cooler 4 degrees to 6 degrees cooler hypolimnion. In the summer, we're setting up a thermocline, which is separating an epilimnion from a hypolimnion. If we look at transmissivity or turbidity, it's interesting that there is a turbidity peak directly below that thermocline. Here we have halite precipitating, creating that greater turbidity. There's halite rafting descending through the whole water column, but there is a halite saturation occurring at that transition as we cross in the summer from the epilimnion into the hypolimnion. There is a turbidity peak directly below the thermocline related to increased summer precipitation of halite. Sirota and others have done a lot of work in terms of the upper and the lower brines. What's interesting, if we look at the temperature profile in the upper chart, the salinity profile, and we look at their differences between the upper brine and the lower brine, we can see in the summer, the upper brine is much warmer than the lower brine. The lower brine temperature doesn't oscillate much. It's around 24, 25 degrees, whereas the upper brine temperatures increase in the summer up to 34 degrees. But then in the winter, they equilibrate, they homogenize, we lose the metalimnion, and then we go back into spring and summer and we see that separation again across the years 2014, 2015, and 2016. Likewise, if we look at salinity, we can see that the salinity in that upper warmer mass is greater than in that lower water mass, the hypolimnion. But if we look at the halite saturation state in that upper column, remember that halite is a prograde salt, and we're looking at a relatively homogeneous holomictic water body. That upper hot of water actually becomes undersaturated with respect to halite. So that upper brine, as we follow that halite saturation curve across, that upper brine is undersaturated because it's hotter in the summer than it is in the winter when it becomes supersaturated. So if we look at the crystallization rates now in the lower chart between the upper brine at a depth of 10 meters and the lower brine at a depth of 50 meters, and this was measured using that crystallization cable, we can see that in the summer there is little or no growth on that crystallization cable in that upper section of the column. But when we pass into winter, there is crystallization on the whole column from the brine surface all the way down to the bottom. During summers, the epilimnion is undersaturated, and so halite, in effect, is dissolved, whereas in the winter, the entire brine column is supersaturated and crystallizing halite. This leads to a mixing mechanism documented here for the first time, which is a significant one for ancient halite bodies as well, known as double diffusion salt interfingering. Those images are showing you that cable at a depth of 10 meters and a depth of 30 meters in the summer. So the 10-meter depth is in the epilimnion, warmer water mass, and the 30-meter is in the hyperlimnion. In summer, there's no crystallization on that cable. It's undersaturated with respect to halite because it's a prograde salt and those surface waters are warmer. Whereas below the thermocline, in the hyperlimnion, we have saturation throughout the summer. So in the summer, in shallow waters, in that 300-meter deep brine column in the Dead Sea, those surface waters are undersaturated. We'll see that a little later when we look at what's happening around the margins of the Northern Basin in those mixed sedimentation environments. But in the brine column in the deeper water section, it's important to note the upper water mass is undersaturated in the summer. The lower water mass is maintaining its halite saturation year round. There must be some type of interfingering between the upper and the lower brine masses at that metalimnion in the summer. It's going to be driven by that contact between that warmer, saltier and denser water, which will want to sink into the underlying column, and that cooler, less salty water in the water below. We're going to mix warmer, more saline saturated upper water brine with cooler, underlying, supersaturated, at halite saturation, lower brine in the summer. So we'll see this seasonal precipitation of halite at the thermocline. In the summer, we're driving precipitation of halite not in large volumes in that upper water mass, but at the thermocline. We see silt-sized halite along with the rafts that are forming as background sedimentation sinking through that saturated deep bottom, and in the summer we form this fine cumulate layer in amongst those coarser bottom halites. There's background halite saturation with meshworks forming, but in the summer we form this finer crystalline halite at the metalimnion sinking to the bottom. In the winter we see clear crystalline meshworks. This is all predicated on the observation that halite is a prograde salt. We have double diffusive salt fingering modelling where QT in that lower set of diagrams on the left-hand diagram is indicating saturated conditions. What work in the Dead Sea has shown is that we're getting double diffusion salt crystallization where we see a mixing across the metalimnion, across that thermal contrast. We are driving in what are the red fluid parcels, initially in the epilimnion. As they sink into the underlying hyperlimnion, they're losing heat. They're maintaining their salinity levels. So they become supersaturated with respect to halite. And we form this finely crystalline halite phase at that metalimnion, which sinks to the bottom. What we're seeing is that saturated brine intermixing with undersaturated brine across that metalimnion. If we think of it in terms of what's happening to the brine masses, and we'll plot it by these red points in the undersaturated summer brine sinking down to become saturated brine versus the saturated brine in the dark blue intermixing with undersaturated brine. So we're setting up convective cells at that interface. We see a sharpening of the metalimnion from what is a 20-meter wide transition in the early summer into a staircase, ultimately in the mid to late summer merging to a single sharp sub-meter step, starting in the midsummer, which is synchronous with increasing salinities and temperatures. We get in this region of double diffusion active halite crystallization, whether we plot it in terms of height and temperature, as in the left-hand lower diagram, or in terms of salinity, or in terms of density. In that interface, we are precipitating halite. At that contact between the epilimnion in the summer and the hyperlimnion, in the epilimnium upper brine, we have warm, saline, but undersaturated waters. Then in the hyperlimnium, it's mixing with cooler, less saline, but supersaturated halite waters. That is driving precipitation through double diffusive mixing across that interface, where the prograde nucleation of halite is occurring in those descending brine fluids as they cool. Arnon and others modelled this interface, where we have this double diffusion salt fingering at the thermocline. The white indicates the descending epilimnion brines. The clear, deeper blue indicates the rising, relatively rising, saturated, but cooler hyperlimnion waters. And in those interfingering zones, we get this double diffusive driven precipitation of fine-grained halite during the summer. This evaporation will seasonally charge the deeper basin each summer with a finer crystalline phase of halite precipitating at that metallimnion interface and sinking through the hyperlimnion, delivering dissolved salt from the undersaturated epilimnion into the halite-saturated hyperlimnion. Each summer, this seasonal undersaturation caused by increasing temperatures above the metallimnion means the upper brine can partially dissolve any halite deposit that it comes into contact with around the edge of the basin, while the deeper basin continues to accumulate halite. This drives a process called halite focusing by Sirota and others back in a paper in 2018. It means in those perennial sump regions below a supersaturated lower brine mass, they're going to tend to accumulate more halite as a combination of cumulates and inclusion-free meshworks in the basin's sump. So over time, we develop this precipitative focus into a basin scale increase in the halite layer thickness in the sump regions, in the deep water regions, below what is a seasonal thermocline. That's at the expense of the halite sitting above that thermocline, which is undersaturated with respect to halite because of its prograde nature in the summer. In effect, we're going to move or focus our halite into the lower parts of that basin. The halite focusing mechanism is obviously hydrologically driven by the effect of summer heating atop the metahalite. In my mind, this raises a question of how relevant is the Dead Sea setting to ancient hydrologies that characterized megaevaporites. In other words, how widespread and relevant is the Dead Sea in its current hydrology to an ancient megaevaporite deposit? We saw that the Dead Sea is a steep-sided continental drainage basin, fed most of its brine by the dissolution of an underlying and nearby halokinetic salt mass. It's relatively small scale. It's not anywhere near the scale of ancient megaevaporites, as we discussed earlier in the course. And tectonically, the Dead Sea is a relatively narrow, rapidly subsiding pull-apart basin. It's in effect a salt-filled chasm where we are dissolving an underlying halite unit. So you have to ask the question, is the equilibrium hydrology in this transform relevant to the types of water depths that would have been at equilibrium, hydrological equilibrium in terms of inflow versus outflow, in an ancient perennial plate edge sub-sea level basin versus this halite-saturated chasm? An ancient megaevaporite was hydrographically isolated. It was typically marine fed. We might have had drawdown of the order of a kilometre, but we reach an equilibrium point where water loss versus water inflow. We don't have this steep-sided focusing that we see in the Dead Sea in terms of its feed hydrology. So how relevant is the Dead Sea transform pull-apart basin to a plate-edge Messinian Mediterranean or an Apnian Atlantic megahalite? Well, I think that's a question that needs to be addressed. The problem that we have is how much texturing do we see preserved in ancient megahalite basins? We need to ask the question, how much chevron halite that's indicative of relatively shallow water conditions, oscillating and fluctuating hydrological conditions, how much was once present in an ancient megahalite basin? That's a highly problematic question, as we'll see in a couple of modules' time, because most of the halite we see in the subsurface has been recrystallized. So we lose that chevron texture and we end up with mosaic and biaxially stressed textures, especially if we're looking at halokinetic salt in many megahalite basins. Deep water focusing of salt below a metallimnion is an interesting concept. I don't think yet our hydrological models are mature enough to take a direct approach and say this is relatively widespread in ancient megahalite basins. It's a question that needs to be addressed in future research.